Now, I rounded to 2 decimal places. I actually got 0.83516 on and on and on. Why did I round to 2 decimal places? That's what they gave me. They gave me data that was rounded to 2 decimal places. So traditionally, if you start with 2 decimal places, you round to 2 decimal places. All right, so now the answer is pretty easy. I take 2, I multiply by sine of theta, that's 0.55. I multiply by cosine of theta, that's 0.84. And my calculator tells me the answer is 0.924. I probably should just put 0.92, shouldn't I? I should put 0.92. Again, if I started with 2 data points in my 2 decimal points in my data, I should probably only give 2 decimal points in my answer. You're absolutely right. I should go to 2 figs. Again, if you're taking a test or a quiz and you roll 0.924, I'm not going to mark it wrong. If this were a physics class, I would mark it wrong because physics is very sig fig crazy. But math people aren't so sig fig crazy. All right, how about part B? Cosine of theta over 2. What would you do there? That's a half angle identity. How do you know that's a half angle identity? Because it's theta over 2. It's the angle divided by 2. All right, so I look up my identity. It has plus or minus square root of 1 plus cosine theta over 2. Once again, I have to ask the question, should I use the positive square root or the negative square root? I'm using the positive.
So that's the directions.
It says in the directions theta is in quadrant 1, but where's theta over 2? It would still have to be quadrant 1, wouldn't it? Because if theta's between 0 and 90 degrees, theta over 2 would have to be between 0 and 45. So I'm still in quadrant 1. All right, so all I have to do is plug in my numbers. This is square root of 1 plus 0.84 over 2. Unfortunately, I have to use the 0.84. Unfortunately, I have to use a number that I calculated. No way around it. We deal with it. All right, so again, I would grab my calculator, I suppose. 1 plus 0.84 divided by 2, and then do the square root of the whole thing. I get 0.96.
So you don't want it in that answer. You want it
Again, on a quiz or a test, I would accept either. But I've noticed I'm looking at the directions, and it just says evaluate. It doesn't say leave in an exact form. So I think in this problem, again, because they gave us a decimal to begin with, a 0.55, it makes sense to give an answer as a decimal 0.96. Okay, but again, if you left it like this as the square root on a quiz or a test, I'd be all right with that. All right, and then the last one, really nothing different. The only difference is this formula has a 1 minus cosine theta over 2. Square root of the whole thing. We're still in quadrant 1, so again, I still pick the positive square root. I grab my calculator, I type all that stuff in, and I got 0.28. Questions on that? All right then, flipping to the backside. Simplify each of the following. Any thoughts on what to do with part A? Well, I don't know. We got lots of identities we can use. A whole big list of them here. Any thoughts on which one we might want to use? Which one? The half identity, why are you thinking you want to use the half identity? Because it's got an x over 2, doesn't it? It's got a half angle. All right, that makes sense to me. So looking at that half identity, it has cosine of x over 2 is plus or minus this whole square root thing. All right, so we don't know anything about x, do we? We don't know which quadrant we're in. So should I use the plus square root or the minus square root? I should use both. That's correct. And the good news is it's not going to matter. How come it's not going to matter? Because after I use that identity, I'm going to square it anyway. All right, so this is going to be 2. The 2 just stays there. I'm going to use the identity for cosine of x over 2. That's plus or minus square root of 1 plus cosine x over 2. But then I need to square that entire thing anyway. So what happens when you square a plus or minus thing? One, it gets rid of the square root. And what's it do with the plus or the minus? It makes it plus 2, because when you square a number, you always get a positive answer or 0. Or 0 squared is 0. So the plus and minus really doesn't matter. All right, so this becomes 2 times 1 plus cosine x over 2. The squaring gets rid of the plus or minus. The squaring also gets rid of the square root. Well, that's better. And then what do? You can reduce the 2's. And your final answer is 1 plus cosine x. Questions on that one? Lindsay.
Why did you write 2 times 1 plus cosine? Wouldn't it be 2 plus 1?
Well, this 2 was originally being multiplied. So I have the 2 multiplied by that whole thing.
So it's not plus or minus, it's positive or negative?
Right. It's not add or subtract. It's make it positive or make it negative depending on which quadrant you're in. Yeah, that's a good question. That's not add or subtract. So maybe plus or minus wasn't the right words to be using there. Make it positive or make it negative depending on which quadrant you're in. All right, how about B? Any thoughts on what to do with B? Well, the first thing I might do with B is I'm going to write it as 2 over secant squared x minus secant squared x over secant squared x. Just split it on the numerator there. One of those is very nice. Secant squared divided by secant squared, that's very nice. That's 1, of course. What about 2 divided by secant squared? What else can you tell me about secant squared? Especially with secant squared down on bottom. It's cosine, right? That's one of our very first identities. One of our very first identities was if you have a secant down on bottom, it's the same as a cosine up on top. So what if you have a secant squared down on bottom? It's a cosine squared up on top. All right, so that's what I think I want to do with that one. I'm going to write this as 2 cosine squared x minus 1. Can I do any better than that? Yes, I can. What can I do better? That happens to be one of the formulas for the double angle identity for cosine. Cosine of 2 theta is 2 cosine squared theta minus 1. So I think my final answer here would be cosine 2x.
from the first step to second step to the two cosine squared for this one?
This one?
Yeah.
All right. So secant squared divided by secant squared, that's
Cosine squared. Wait. 1.
anything divided by itself is 1. And then this side, I have the 2. And then I know if I have a secant down on bottom, that's the same as a cosine up on top. So a secant squared down on bottom is the same as a cosine squared up on top. So the 2 stayed, and I brought that up to the top and switched it to a cosine squared. All right, let's take a look at number 4 then. Number 4 says, determine an identity for sine of 3x. We have a formula for sine of 2x. How about sine of 3x? And it says, hint, write sine of 3x as sine of 2x plus x. Well, how is that going to help? How's it going to help to write sine of 3x as sine of 2x plus x? Which identity could I now use? Sum of two angles. Sine of 2x plus x. All right, so this would be sine of 2x cosine x plus cosine of 2x sine x. Now, typically what we want is we want everything to just have x's in it. We don't want our angles mixed and matched here. We don't want an x here and a 2x there, and 2x there. Typically we want x everywhere. What can I do with this sine of 2x? That's my double angle identity. Sine of 2x is 2 sine x cosine x. All right, so this is 2 sine x cosine x, and then I still have this other cosine, so times cosine x, plus, how about this one? Cosine 2x. Well, cosine 2x, I've got 3 choices. Which one do I pick? The last one. Why the last one? Why not the last one? Would be a good question too. I think what we want to do, however, I'm looking ahead a little bit. This has a sine in it. This is sine x. This is going to give me a cosine squared. What could I do with a cosine squared? I could use my Pythagorean identity and write that using a sine. This has a sine. So what I'm looking ahead at is this has a sine. Cosine squared I can write using sine. This one's a sine. I think I'd like to use the one that only has sine in it. I think when I get all done, I'm going to be able to write my answer only using the sine function. So I think for cosine 2x, I think this time I want to use 1 minus 2 sine squared x. So this is 1 minus 2 sine squared x times sine x.
Could you use another one?
I could use another one, but it would be more steps, because then what I would want to do is I notice I have lots of sines, so if I used a different one, I would then have to take that one and convert it to only being sines in it. All right, so 2 sine x times, this would be cosine squared x, but how can I write cosine squared x only using the sine function? 1 minus sine squared. That's one of my Pythagorean identities. Cosine squared is 1 minus sine squared. So I can write this as 1 minus sine squared x plus 1 minus 2 sine squared x times sine x. And then finally, I think I'm going to distribute here, and I'm going to distribute there. Oops, I wrote 6 instead of sine x. Distribute here, distribute there, and then combine up all my like terms and see what I have. All right, so that would give me 2 sine x minus 2 sine cubed x plus, distribute here, that's a sine x minus 2 sine cubed x. So it looks like a final answer could be minus 4 sine cubed x plus 3 sine x when I combine my like terms. Questions on that? Could you do the same thing for cosine of 3x? Absolutely, if you wanted to, you could find a formula for cosine of 3x. Could you find a formula for cosine of 4x? What would you do for cosine of 4x? You could write it as 2x plus 2x and work it all out, so on and so forth. So could you find a formula for any of these? Sine 5x, sine 6x? Yeah, what happens? They get long and ugly. That's right. I mean, this is already kind of ugly. If you go 4x, 5x, 6x, you can find formulas for them. They get pretty long and ugly is the only deal. All right, well, I have very, very good news about section 7.3. Well, I'm not going to say that it's easy, because I don't think it's easy. But what I am going to say is it's nothing new. Basically, here's what we did. Here's what we just finished in section 7.2. In section 7.2, I would give you sine theta plus cosine squared theta, and I would say simplify it. Now what I'm doing is I'm telling you sine theta plus cosine theta whole thing squared. I want you to simplify it. And when you get done, your answer better be 1 plus sine 2 theta. So it's really the exact same thing we just did, except I'm telling you what the answer should be. And these are called identities. Well, what's an identity mean? We have lots of identities. What do all these identities mean? What's the definition of an identity?
They really are.
They really are what? They really are formulas that are always true. It doesn't matter what number you plug in for theta or for x and y. In any of these formulas, they're always true. So basically what we're going to do in section 7.3 is we're going to prove a whole bunch of more formulas. So the first formula we're going to prove that sine theta plus cosine theta squared really does equal 1 plus sine 2 theta. And the way these usually work is you start with one side or the other. You start with the left side or you start with the right side. Generally, which one you start with is the one that looks more complicated. So for this problem, I decided that the left side looked a little bit more complicated. So I'm going to start with the left-hand side. I'm going to start with sine theta plus cosine theta whole thing squared. And I'm going to do a bunch of steps. I'm going to do some algebra, do some trigonometry. And when I get all done, I know that I should get the right-hand side. I should get 1 plus sine 2 theta. Well, what would you do?
You have to FOIL it out.
You FOIL it out. All right.
Sine squared theta
Plus 2 sine theta cosine theta plus cosine squared theta. All right, so there's some algebra.
Then use the identities.
And then I use my favorite identities. What are my favorite identities for this problem anyway?
Sine squared theta plus cosine squared theta is 1.
Sine squared theta plus cosine squared theta is 1.
Then you can use the double angle to get sine theta.
And that's the double angle formula. That's exactly right. So there's basically what you're going to do. You're going to start with one side. You're going to do some work. I can get that to focus better. Until you end up with the right-hand side. All right? So very common things that happen in almost all of these identities. You use the Pythagorean identity a lot. So look for that one a lot. 2 has a common thing that happens a lot. In 2, we see we have a whole bunch of fractions. What are you going to do when you have a whole bunch of fractions? You got to add some things there, don't you? How do you add 2 fractions? Common denominator. That happens a lot in these problems. All right, so for number 2, again, I looked at number 2 and I said, well, to me, the left-hand side looks more complicated. Do you agree that the left-hand side looks more complicated? Yeah, all right. So I start with the left-hand side. 1 plus cosine theta over sine theta plus sine theta over cosine theta. I notice I'm trying to add a couple of fractions. In order to add a couple of fractions, I better have common denominator. What's the common denominator? I just multiply them together, sine, cosine. Sine theta, cosine theta, plus sine theta, cosine theta. Okay. The first fraction, I multiplied the bottom by cosine, so I better multiply the top by cosine. What do I get when I take this top and I multiply it by cosine? Cosine theta plus cosine squared theta. Multiply, so this first fraction, I multiply top and bottom by cosine. So I have to take this cosine and distribute it through. Second fraction, I multiply top and bottom by sine theta. So up on top I have sine squared theta. Now I can add my fractions together. When I add my fractions together, what do I get? Cosine theta plus 1. Why do you get cosine theta plus 1? There's the Pythagorean identity again. So far we've done 2 problems. We've used that identity twice. This is cosine theta plus 1 divided by sine theta cosine theta. Is that what I'm supposed to have? Yes, it is. So I'm all done. That's what I'm supposed to have on the right-hand side. All right, number 3. Number 3, first we decide which side looks uglier, the left-hand side or the right-hand side? Right. The right-hand side. All right, so we're going to start with the right side. That's cosine to the 4th x minus sine to the 4th x. All right, what can you do? You can break it up into difference of perfect squares. Excellent. This is, it factors cosine squared x minus sine squared x times cosine squared x plus sine squared x. That's the difference of perfect squares. Because cosine to the 4th is cosine squared squared, and sine to the 4th is sine squared squared. Okay, great start. Now what?
One of them equals 1.
One of them equals 1. Which one?
The right side.
The one on the right. Cosine squared plus sine squared equals 1. And how about the one on the left?
Oh, that's double angle.
That's a double angle. Now, am I surprised that I ended up having to use the double angle formula for cosine? No, because look at what my answer should be. My answer should be cosine 2x, which tells me that at some point I'm probably going to have to use a double angle formula for cosine, and that does happen to fit. Cosine squared minus sine squared happens to fit into the double angle formula for cosine. So this is cosine of 2x. Cosine of 2x times 1 is cosine of 2x, and I did end up with the left side. You could have used left side first, absolutely. How would you have done it if you used left side first? I think it would be trickier. Because I think what you would do, to use left-hand side first, I think you would go ahead and you would use the double angle identity. And you might write this as cosine squared x minus sine squared x. But then I don't think it's very clear or very obvious how are you going to get those to be cosine to the fourth minus sine to the fourth. If I square them, I would have to do FOIL. And I would end up with some of the two middle terms there. And besides that, if I square this side, I also have to square that side, and I don't want to square that side. I think you would have to be really clever here to recognize what I'm going to do is I'm going to multiply this by the number 1, but I'm going to write the number 1 in a funny way. Here's how I'm going to write the number 1. And then you would go ahead and do FOIL, and you would end up with your... So it's really the same thing we did, it's just working backward. But I think you'd have to be pretty clever to think, I better multiply by that to get the cosine to the fourth and the sine to the fourth. I think in this problem it's easier to start with the right-hand side. And I think the right-hand side to begin with is a little bit more complicated. That's generally where you want to start. You want to start with the more complicated looking side. All right, so keeping that in mind, problem 4. Would you start left-hand side or would you start with the right-hand side? I think the left certainly looks more complicated to me, so I'll start with the left. Cosine of u minus v divided by cosine u sine u, or cosine u sine v. Cosine u sine v. All right, what can you do? Distribute the cosine? No, you can only use, when can you use the distributive property?
Only with a square. No.
Tell me the distributive property. We all know the distributive property. What does the distributive property say? When can you distribute? Only once. What operation allows you to distribute? Multiplication. Is cosine a multiplication thing? No. So if this was 5 times u minus v, then I could distribute. But this is not a multiplication. This is a function notation, so I can't distribute. What can I do with that? I can use the difference identity, cosine of u minus v. All right, so let's try that. That's going to be, according to that formula, it's cosine u cosine v minus, oh no, it's plus, isn't it? Plus sine u sine v. And then I'm going to divide that whole thing by cosine u sine v. Now what? I can break it into 2 fractions. I can break it on the numerator. Okay. Cosine u cosine v divided by cosine u sine v plus sine u sine v over cosine u sine v. I like that because I think I can reduce some stuff. What can I reduce? I can reduce cosine of u with the cosine of u in that fraction. And how about the sine of v with the sine of v in that fraction? All right, what am I left with? Cosine v over sine v. Write that another way. That's cotangent. Cosine over sine is cotangent. It's cotangent v. And how about sine of u over cosine of u? That's tangent of u. Is that the same as the right-hand side? It is. written in the other order, but we can switch order, can't we? All right. 2 more to go. How about number 5? Start with the left. All right. I would agree that the left is more complicated. Cosine theta plus sine theta over cosine theta.
Could you break that up?
Break it on the numerator, just like we did last time?
Yeah.
Absolutely. Cosine theta over cosine theta plus sine theta over cosine theta. Cosine over cosine is 1. Sine over cosine is tangent. Oops, hit the crack there. The end. That was the easiest one on the whole sheet, I thought. All right. Conversely, I think number 6 is probably the hardest one on the sheet. It's got an interesting trick to it. All right, what would you do on 6? The right-hand side? Maybe. The left-hand side? Maybe. You get a 50-50 chance of being right. I'm going to start with the left. And I'll show you why. This happens in a lot of these identities, and this is something to watch. If you see a 1 minus cosine theta, or if you see a 1 plus cosine theta, or a 1 minus sine or a 1 plus sine, this is a very common thing you're going to do. Can I split this one like I did the previous two? No, you can't split on a denominator, unfortunately. What you're going to do, if you see a 1 minus cosine, you're almost always going to want to multiply top and bottom by 1 plus cosine. Conversely, if I saw a 1 plus cosine, I almost always want to multiply top and bottom by a 1 minus cosine. Why? Well, what do you get down on bottom when you FOIL that out? You get sine squared. Excellent. Because when you FOIL it out, we're using, what's the fancy word for when you change the sign in the middle? One's a positive, one's a negative. Not negative reciprocal. Conjugate is the fancy math word for change the sign in the middle. That's correct. When you multiply by the conjugate, the middle terms cancel out. When you do FOIL, you end up with a 1 minus cosine squared, and 1 minus cosine squared is sine squared. So what we're doing when we see this, we're setting it up, we're multiplying by the right thing to allow us to use that Pythagorean identity. And again, that Pythagorean identity shows up in almost all of these problems. It didn't show up in 4 and 5, but I think it showed up in all the other ones we did. All right, up on top, I guess I'll just distribute. That's going to be sine theta plus sine theta cosine theta. All right, so this is sine theta plus sine theta cosine theta divided by sine squared theta. Now we're almost done. What can we do now?
Could you break it up?
Now I can split on the numerator. You can split on the numerator when you have an add or subtract, but not on the denominator. So I'm going to split it up. That's sine theta over sine squared theta plus sine theta cosine theta over sine squared theta. I do a little bit of reducing. One sine cancels with one sine, and one sine cancels with one sine. And what am I left with? What's 1 over sine theta? That's cosecant theta. And how about cosine theta over sine theta? Cotangent theta. And that is the right-hand side. Again, it's simply written in the other order. We can switch order. All right, so that's a very, very common trick. Again, if you see a 1 minus cosine, you're going to multiply by 1 plus cosine. If you saw a 1 plus sign, you want to multiply by a 1 minus sign. Use your conjugates.